Hello and welcome for another episode of Profiles in American Funded Research. I'm excited to have my guest, Shibaji Chakraborty. And he got a bachelor's degree at the Institute of Engineering and Management, a master's, multiple masters actually, at Virginia Tech, a PhD at Virginia Tech, did a postdoc at Virginia Tech, and now is a research scientist at Embry-Riddle. Is everything correct there?
Yeah, that sounds good.
Uh, Awesome. And I invited Shivaji on today to discuss modeling ionospheric and magnetospheric current interactions with submarine cables, a project that he recently got. So could you give us a brief overview of the project?
Yeah, thanks, Jeremy, for having me. So the overview of the project is it's like understanding the impacts of the space weather. So just like so, before introducing the project, I think I need to clarify some of the wordings or like the nomenclature. Otherwise, the definition of the project might sound haywire, like you don't understand what is going on. So there is a specific term called space weather. It's a scientific terminology. It's just like the terrestrial weather you have. You can have the similar type of weather up in the atmosphere where the atmosphere is not only governed by the gases, just like the lower atmosphere, but also governed by the electrical currents and voltages. It is the charged and magnetized part of our atmosphere. So over there, you have different sorts of weather. We call it a space weather or geospace environment. So most likely these geospace weather is controlled by the sun and solar wind, which is like the most like powerhouse of our solar system. And then it the currents that are moving there, and that sort of altitude can altered by the solar wind and the sun, and that current which is introduced by the solar wind or the sun or maybe some other processes in within the system itself, the geospace system, that can interact with different sort of instrument which is on the ground, definitely on the space. For example, if you send someone to ISS, International Space Station, you have to worry about the uh, different sorts of radiation and other things coming from the sun. You have to know this. So that is one example. The second example is like the space weather can also impact the system on ground, what I just mentioned. For example, transformers, which are like transmitting, let's say, thousands and millions of volts, like from one end to another end. Like for example, one like from, let's say, a power grid in Texas that is actually transmitting power to, let's say, in Nevada or maybe somewhere else that right beside other states. So that's like thousands of, not thousands but hundreds of kilometers, or sometimes it can go across the border and it can create significant long distances. And those wires, which are like significantly like they are located significantly higher distances, longer distances, that can be impacted from these current systems in the atmosphere. So that's one of the upper atmosphere or space weather. So that's one part. And then you can have long conducting wires underneath the water bodies as well. So that is my field of study, or maybe you can think about this is one part of my field of study, which is like how that currents can also impact the long distance wire underneath the water, which is submarine cables. So why? So now the thing is that why it is important. Most of the things whenever you open up Twitter, Google, Gmail, or whatever, if let's say most of the servers are in either Europe or China or USA, right? I mean, most of the big tech companies are situated somewhere over like northern part of the America, or maybe in the eastern western Europe, or somewhere in the China. So whenever you open an app, whether it's a laptop, your computer, or maybe even like your mobile, it actually tries to go to that specific server. And the communication itself, like if it is a local server, then it's a quick enough, like you can go through fiber optics within the land and underneath the like earth or something, or like land. And but the thing is that if you want to, if you're sitting in the Europe, Western Europe, and if you want to connect a server in, let's say, X, right? I mean Twitter, formerly Twitter. So what happens is like your connection go underneath the communication channel is underneath the wire, underneath the water, and that actually like 7 or 8 thousand approximately, depending upon where you are located, 7 8 thousand kilometers. And whenever a significant changes happen in the space weather, that creating a kind of Faraday effect. I'm not sure that's too much of a jargon. Faraday law. Probably people from at least high school can understand what is Faraday law is, and so Faraday laws get impacted, and the conducting wires can introduce significant like another body of current source which is outside of that integrated system, right? I mean, that specific current is not coming from the terminals of this wire where they are connected in the either side of the continents, and that can disrupt not only the signal, it can severely damage the cable, the power feed systems. And as you can see, like those cables are going underneath the water. Sometimes it's like it can be like 4 or 5 kilometers where you can't like have someone like a scuba diver say just go and fix it. It's not that. And the downtime will be severe, and it can get disrupted for significantly long period of time. So my specific project is to understand the space weather and understand how they are actually these currents, space weather driven currents, ionospheric, magnetospheric currents can actually impact or translate system currents inside these submarine cables, so that you can understand this connection between upper atmosphere and underneath the water. And that actually is a part of geospace study and also space weather study. It's a kind of a, I would put it like a hybrid study of two different region or two different field of study. So that's the primary goal, to understand what is happening, what is the hazard associated to that, and probably forecast something which is like maybe 100 years or 1,000 years even, that can kind of create a significant disruption. And yeah, to understand.
Well, thank you. So, can you explain what the solar wind is and how it generates these currents that we're experiencing?
Well, to answer, so that let us understand solar wind first. I would say like it is relatively easier to explain and understand. So sun is an active star, right? It's not dying star. So there are concept of active star, dying star, different things. So whenever a star is an active state, so it shoots out. It's a ball of plasma. Plasma is a fourth state of matter. If you can think about it, if you superheat something, first state is solid. The molecule get disintegrated, it becomes liquid. Then the third state become gas, and the fourth state is like whenever the gas is become ionized, it's called plasma. So one example of plasma is fire, for example. So whenever you light something, let's say you go for a camping and you fire something up, that's fire is a plasma. So sun is itself is a plasma ball. So what happens is like whenever, so there are different sort of phenomena happening on the surface of the sun, inside the sun, and also the surface of the sun. So just like the storm on our surface, like for example hurricane or maybe tsunami, tornadoes, these are these type of geophysical phenomena. Sun has similar type of on its surface, it has similar type of phenomena. So there are different nomenclature in that, but cumulatively people call it a solar storm. So whenever it happens, so it shoots out plasma towards like the other planetary bodies within the solar systems. So those plasma and also so sun because if you so again, like there is a fundamental concept in Maxwell's equation. Whenever if you have a charged body and if you rotate it very fast, you can create magnetic field. It's Ampere's law, right? I mean, fundamentally, if you have a charged body, a similar thing is like that. Is like sun. It in itself has some magnetized magnetic field. So because it's a plasma, it's a charged body, and if you rotate, sun rotates in itself in its axis. So it has a magnetized field, and that magnetic field actually it can actually go outside the body of the main body of the sun, and the plasma along which is frozen inside those magnetic field can also travels in the interplanetary systems. So together these two systems, which is called interplanetary magnetic field and the solar wind, which is like the plasma or matter, I'll simply say this, the charged matter coming from the sun, these two are the primarily governing body of the solar wind. So anything coming from the sun, and I just mentioned like whenever something happens on the sun, it shoots out. It's not necessarily like that. I'm just exaggerating a typical scenario. Even if nothing is happening, a sun is a very quiet. There are things that can actually shoots out this charged matter or plasma towards the Earth or maybe other planetary bodies, and that is actually called solar wind. So that specific wind, we that's a charged and magnetized um, particle. I'll put it that like that.
Yeah, can you discuss, since we're on the topic, coronal mass ejection?
Yes, yeah. So that's a very specific event. So I said like there are different geophysical phenomena happening on the surface of the sun, right? So one of them called coronal mass ejection, and then there is a thing called solar flares. So what happens is like these charged sun is like on top of the surface of the sun. So if let's say a plasma, so sometimes what happens is like so if you look into the sun through X-ray images, so if you look into the visible spectrum, sun looks like it's a very quiet thing. It's a ball of firing something at the visible length. But if you go into the X-ray and UV, you'll see sun is doing some crazy stuff, which is not actually you do see in a regular day towards the sun if you look into the sun. And then what happens is like the coronal mass ejection is a phenomena when sun shoots out significant body of plasma blobs towards the earth. What happens is like this magnetic field that holds, actually what happens is like if you have a charged particle and if you have a magnetized magnetic field, then if you just keep one specific charge into a magnetic field line, it tries to hold that specific position because you can actually trap charged particle through magnetic or electric field. That's the basic behavior of a charged particle. Now what happens is like if the magnetic field, let's say, it's get disrupted for some reason, that charged particle can actually move up and down, basically driven, governed by these magnetic field structures. So similar thing happens on the surface of the sun. Most of the outer shell of the sun is protected by its own magnetic field structure, but sometimes there are pressures, tension happening in those magnetic field line, and that gets actually it's not exactly scientifically happening. If I use the word is like get tear, like those things actually shoots out, so the magnetic field lines get actually displaced, I'll put it like that, and they get ruptured. It's not actually rupturing something, it sounds like rupturing, but it get tears and it actually shoots out those plasma particles with very high speeds, and that's called CME, or coronal mass ejection. It happens on the coronagraph, which is the atmosphere of the sun. So that's why it's called coronal mass ejections.
And when there are CME events, do we is that can you like see aurora in the atmosphere?
That's again, yeah. There are so aurora. So okay, so aurora does not direct. It's not a one-to-one relationship between an CME and aurora, but it's like whenever CME happens, if it is get trapped into the, so what happens is like here is the sun, it shoots out the CME. The CME travels through this one the distance between sun and the earth, which is like 1500 miles, sorry, 1500 million miles from earth and sun, and that actually travels through that interplanetary space. And then what happens is like sometimes it get actually the earth get missed by it most of the hit. So there are CMEs happening on the regular day, but we don't actually get hit by those CMEs. So what happens is like if a CME hits the earth, it actually first hits the magnetosphere, and then it actually comes down to the both the poles of this magnetized through this magnetic field line of the earth, and that actually can create an aurora. Most of the times yes, but there are certain times there are no visible, I'll put it like visible aurora, because aurora is in itself nothing but um those charged particles come down through the magnetic field line on the either side of the pole of the earth, and it can actually create radiation as a secondary radiation on the atmosphere gases like oxygen, or let's say hydrogen, helium, something like that, or maybe NO, which is nitric oxide. Those are present in our atmosphere, and that get illuminated. So, but sometimes what happens is like those are the visible aurora. You can actually see them in your naked eye. If you have no light pollution, you can see them. But there are sometimes, depending upon the energy or the wave bands, or maybe the excitation state, I'll put it like that. Maybe this is again a jargon, but sometimes these radiation, re-radiation of this atmosphere happens in the domain of the wavelength where it is not fall in our visible wavelength. So that might also happen. So most of the time, so all the time aurora happens, some of them are visible, some of them are not. I'll put it like that.
Nice. Okay.
To give you an example, I'm not sure whether you heard this 2024 May event. May event 2024 May, there was a strong CME or solar storm happening. So people observed aurora in Florida or in Texas. If there are, so you can actually, I'm not sure you know this, but if you Google it, like people observing 2024 May solar storm driven aurora in the far south, you can see like people in the even in the Mexico reported that. So yeah, if it is a very strong storm, you can actually see aurora, or the CME is really powerful. You can see aurora near the southern state as well. Yeah.
Now, how much does the magnetosphere protect us from these events? The Earth's magnetosphere.
Yeah. Um, so the Earth magnetosphere protect us how much? If I put it like that, it's almost 99.99%. It so what happens is like the whenever there is a charged particle, you can actually protect or create a barrier between you or maybe living organism and those heavy radiation which you can get a cancer of, right? I mean, so put it like this. So if I keep you in the outside of the or not even in the outside of the magnetosphere, even in the ionosphere or magnetosphere, maybe 1 hour dose is significant enough to create cancer. So you can think about it. So the magnetosphere it in itself protect those charges by streamlining, because it's a magnetic field lines or magnet. So you can actually um, repel some of this, most of the charges coming from the sun on the either side of the earth, or maybe not directly on the surface of the earth. You can redirect it far away from the surface of the earth. And then comes, there is a region, there are multiple regions in technological, like when we study science, there are a lot of different regions in between that. I grossly modify it like magnetosphere, thermosphere, ionosphere, and then maybe you can think about mesosphere. So from the magnetosphere, there are some part of this magnetized plasma can actually penetrate through this magnetic field line to the ionosphere. It again, like it is again a significantly charged electrical part of the atmosphere, which again like act as a shield. So that again like protect us from some of these. And then there is a mesosphere, ozonosphere. They also protect us. It's like a filter, right? I mean, things coming us from the sun, you have one filter, you can think about it, magnetosphere, it filters significantly. Then the ionosphere, mesosphere, ozonosphere, yeah, you have a thick layer of different layers of filters between you and the solar wind. So most of the living organism, we have no worry about this charged particle. Yeah.
Great. So
Give you an example. Sorry, just sorry to cut you on. So again, so I'm not sure you. So you see, like recently, two astronauts came back from the ISS. Have you seen that? So go ahead, if you Google them, go ahead and check their hair color before 1 year and now. So you'll see what I'm talking about. Space is a very 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 harsh environment where the aging itself, even if you are protected by so many layers, this small leaky radiation can actually increase your aging significantly. So you can see the difference between if you just check their skin tone and also the hair color, the grayness of the hair. You don't see like a people age in a year certainly like that if they're in on the on surface of the earth or maybe somewhere in the ocean. They don't do that. So that's again an example of what I'm talking about.
so now you discussed that there are multiple layers, obviously protecting us from the charged particles.
Mhm.
But what is the issue that you're studying here, right? Because it must not be exactly the charged particles, but something else that is affecting the submarine cables, right? What is this induced current?
So the first thing is like how did this thing whole thing induces current? So what happens is like whenever there is a if you have a magnetic field lines, and if you rapidly change the magnetic field lines, what happens, it creates a current. That's like the second law of Maxwell, or maybe Faraday's law of Maxwell theory that talks about that. And they are significantly large current concerning, given if you are thinking about the magnetosphere, the structure of this magnetosphere and ionosphere. Earth has a radius of let's say 1 RE, which is like 6,400 kilometer ish. But if you think about it, like the magnetosphere, so magnetosphere is not exactly a sphere. It looks like a teardrop shape. So the front of it, like if you front like wherever the sun is, if you think about the direction of the sun, it is like 6 to 10 RE depending upon different things. And if you go on the tail, it's like sometimes 20 to 60 RE, even depending upon various publication you'll see, like, so it's a very large structure. So whenever we are talking about these large structure and currents within the structure, the currents is in millions of amps. It's not like 1 amp, 2 amp, or maybe 5 amps, 15, 20, or maybe even kiloamps. It's a millions, tens of millions, or hundreds of millions of amps. And whenever these currents, so there is a interlinked, if you go back to the like high school again, the Maxwell's equation. So change in the magnetic field lines or magnetic field structure creates a currents, and then these currents can again create induce voltages on a conducting wire or conducting structures. So this whole thing happens in a loop, and that is how the electromagnetic field sustains. So now what happens is like, uh, let's say if you're holding a laptop, right? I mean, and it is charged in your charging cord, which is like few feet, let's say 5 to 10 feet, and a magnetic storm happens, millions of amps or tens of millions of amps are passing in the ionosphere or magnetosphere. Those currents might not significant enough to create a magnetic field or induce a current on your 5 or 10 feet wire. The reason is the structure. The whole concept is it's a relative scale that matters. Now, same thing happens, and if you have wire that is like like probing from one end of the continent to the another end of the continent, which is like thousands of kilometer, right? Then I remember one of my paper that we observed something on the TAT 8 cable, which is transatlantic cable, and that is actually like 7,800 8,000 kilometers or so. That is actually one of the first category of coaxial cables that actually connected Western Europe and Eastern America. And that, so there was a storm which is called Hydro-Quebec storm. I'm not sure general people aware of it. It happened 1989. It's one of a kind storm which is called a superstorm. So there are certain criteria. Then what happens is like if you get hit by a large CME, and if your one of your magnetic field flips beyond 500 nanotesla, so that kind category of storm or geophysical storm, we call them superstorm. Now they can create significant disruption. It's not like, so that's a few hundreds of nanotesla in the scale of thousands of kilometers, or maybe even in the scale of, let's say, few radius of the earth, can create huge disruption when you consider a wire lying on the top of the surface of the earth, which is few thousand kilometers, because of this induction effect. So um, now going back to those days, the cables were coaxial, which is like conducting wire. It's like two conducting wires is like rotating on top of each other, a helical shape, and they are moving from one end to another, and that's a coaxial structure. But right now, after I guess 2000 or late 1990s, I guess, maybe after 1996, or maybe I don't remember exact year or something, but after 95 for sure, and sure after 2000, like after millennia, we changed those coaxial cable to fiber optics because of reliability, because of their performance throughput is much higher. So we actually changed them. But if what happens is like even with this, and the fiber optic cables actually transmit light pulses. They don't transmit electrical pulses. They transmit light pulses and an on and off. Now they don't get disrupted by this current structure because they are beyond these electrical systems. But problem is like these electrical light pulses needs to be filtered and retransmitted after few thousand or maybe few hundreds of kilometers, depending upon where you are. And they needs to be refiltered again and again and again. And these things that does these kind of things, this performance, they call repeaters. They are very well known structure in any telecommunication systems. They call it repeater. You have repeaters few kilometers or few hundreds of kilometers depending upon where you are, and they require to have a power feed cable, and that's a copper cable, sometimes aluminum cable, depending upon what type of cable you are making, and that gets impacted so that the power feed equipment and so on and so forth. Now these new type of cables that I'm describing, they are like they can hold up to like tens of kV to 15 of kV. So even like they're running, let's say 7 kV or so, kilovolts. And those cables, they are running from one end to another end, these copper wire, they are well below these threshold. But what happens is like during these type of phenomena, these voltages across through this cable can go up significantly so that it can actually trip, like which is like a short circuit kind of scenario where huge currents or voltage is passing through this cable. Just like the thunderstorm can actually disrupt your TV, or maybe your computer or something. You need a protection system, surge protection system. It seems something like that. So if you have a large amount of current passing too quickly overhead of this cable, that can create an induction effect, which can induce current on this long distance wire, and they can create um, kind of surge. And there is, as far as I know, there are surge protectors, similar principle, surge protector. But even with surge protector, if you have a significant high voltages, they can trip the wire. That is how I'll put it. So it is the problem of the surge protection versus how much surge protection is needed, and what is the upper limit of it. How should we mitigate the, if it is, even if it is happen, how we mitigate them. So that's the whole idea of this project.
Are these induced currents large enough to create a significant force at all on the cable?
What do you mean by force?
So you can, if you have a current, you can actually induce a force right? Perpendicular. Is it,
Yeah, okay.
are the forces strong enough on the cable to affect it at all?
That's a very good question. I am not exactly sure about that, but we are, I don't think so, because even if the millions of amps is passing on top of the the concept here is like whenever the currents are induced on those wires, right? I mean, this is, we are talking about, let's say, a cable like this big. You can actually Google and see like how the structure are. And most of the cables or the wires passing through that big chunk of this cross section, they are fiber optics, and they are much heavier. And there is maybe a small wire like this big, which is like the power feed equipment I'm talking about. So even if whatever the force is happening, my naive idea is it might not shift this whole structure. That is, I don't think so. But just to give you an idea, the landslide and tsunamis are bigger problem sometimes, like in terms of moving this whole structure or the cables from here and there, or maybe something sometimes like tearing them up, like from in two pieces or three pieces, multiple pieces. So tsunamis and underwater earthquake, they are the much more problematic for these type of scenarios. Not this space weather. I wouldn't. If it happens, that's a groundbreaking science, I'd say. Yeah, we don't expect that much of a repulsive or attractive force.
Now, how does frequency play a role? So the frequency of the signal versus the disturbance, right, that's coming in. Like, does it affect mostly high frequency, low frequency?
Yeah, that's a great question. So as I mentioned, is like there are different layers in the atmosphere, right? So I think it in terms of I am trained as an electrical electronics engineer, so I always think them as a filter stacked on top of each other. So there are other filters too. Air does not play a significant role in filtering those structure because the permittivity and permeability of the air is approximately one, so doesn't make much of a difference. Like normal air, I'm talking about, which is unmagnetized, uncharged. But salty water is again a very good protector, which is the ocean surface we are talking about, big thick layer of water. Now going back to two things, I'll add another point on top of that. To talk about frequency plays a role, yes, absolutely. One of the biggest player that creates a significant modification on that, because whenever you thinking in terms of filter has different filters have different frequency response, and they some of the filters act differently in lower frequency, some of the filter has a different response in higher, some of them band pass, some of them are band reject, depending upon how you think about the filter frequency response of the filter. Now, along with the frequency component, there is, so we normally think Earth as neutral, right? I mean, that is how our houses are built. Earth is a neutral conducting surface. It's ground. That is what we think about. But when we consider like these big structure currents, Earth is not ground anymore. It can actually or these currents whenever they produce, so if you think about it, current cannot, voltage can be open loop, a voltage source, but current cannot be an open loop. Current needs to be feedback into itself. It only exists in a loop. The open, that is how the fundamentals are there. Now if you think about it, a wire which is a submarine cable, a current is flowing from one end of the wire to another end that needs to go somewhere, or needs to go and fulfill the loop. And what happens is like it can fill the loop or from one end to another through the surface of, not the surface, like the bottom of the ocean, because it's in there, bottom of the ocean, it can actually loop in. And now what happens is like this, the different structure of the earth layer can actually play a significant role how they actually can control this return flow of the current. So there are two parameter, which is one of the biggest parameter that controls how much induction can happen, how much filtration in frequency response. It's the frequency, And the second part is like the structure, which is like this, we call it a conductive earth structure, because not all, if earth is not if you think about it, earth crust, and there are different layers, mantle and different layers, so they are not uniformly distributed. It's not exactly a concentric circle of things. If you cut earth half in like an apple, it's not a concentric circle everywhere. It's like one is 10 meter, 20 meter. It's not like that. Radius is not conform uniform. So those actually can play a significant role in how much or which frequency is affecting where. So for example, it's a 8,000 kilometer long wire. In one part, let's say one hertz frequency is really, or maybe 1 millihertz frequency is really creating some impact on the wire. If you go, let's say 1,000 kilometer east, it might be 20 millihertz. So it's a 20-fold difference between these two frequency. So that is how it is. And to answer your first question, coming back, how the frequency, generally what I have seen, and there might be limitation in what my understanding, because I'm still doing it. I don't want to use the exact term, but I have seen with this water in structure, most of the response of this filter I was talking about that creates the frequency response I'm talking. So they are in a form of band pass. So they are not actually, so if you plot them from, let's say, 10 to the power minus 6 hertz to 1 hertz, because what frequency we are talking about, they are not really high frequency, they are very low frequencies. That can create a significant disruption in here. Unlike in in our house, what happens is, like in our apartment or house, if you have a TV, that surge protector is actually protecting you from the high sharp peaks and troughs, right? I mean, going up and voltage if the voltage swing is too rapid. Whereas here, you can think about that that thing is significantly shifted, and the frequency range we are talking about in millihertz or microhertz, something like that. And if you go like below in the range of microhertz, which is 10 to the power minus 6 hertz, the response is very low. It does not create a significant impact. Again, if you go into the higher frequencies, let's say beyond 1 to 10 hertz, most of the time they are not these things are not susceptible to those frequencies. They are mostly impactful between, let's say, 10 to 1 millihertz to hundreds of millihertz. They are most susceptible to. And that is also like, there is a very strong scientific evidence. Like, why is that? Because the reason is, like, these wavelengths, if you think about it, this frequency, you can turn it upside down and create a wavelength. And these wavelengths are directly proportional to the water thickness on top of this cable. So if you have really small water thickness on the side of the cables where they are actually coming out of the ocean, it's called coastal effect. So at those ranges, the coastal effect is like significantly high, because you have smaller, let's say hundreds of meter water depth, and the higher frequency effect significantly predominant over there. But if you go deep into the ocean, like in the middle of the ocean, where let's say the ocean depth is 4 to 5 kilometer, at that point in those regions they are like millihertz because of these scenarios. Does it make sense?
Yes.
That's one way to think about it.
So you mentioned that.
And also, yeah, sorry,
Oh, go ahead. Go ahead.
I think there is a lag in my system.
Go ahead. Go ahead.
Yeah, no, yeah, just to complete that thought, there are two components. Just repeat because I said too many points here. Just to fill it out, 2 points. First is frequency response from water thickness, the frequency of that are flowing in on the magnet. The third, the earth structure or activities or earth structure. These three things are primarily drives what we see on the submarine cable effect.
Okay, so now you mentioned at the beginning that that you are that there are a number of things that can be affected by the underground cables having these injections of currents, these induced currents. So my question is there a way of predicting these events before they happen so that we can kind of be prepared for
That's an excellent point. Yeah, that's an excellent point. Yes, people do study. So primarily what we try to understand is like most likely this geomagnetic storm that is associated with the CME driven structure we are talking about previously, the coronal mass ejections. And there are some other phenomena as well. I'll broadly categorize everything as solar storm. So let's say we try to forecast some category of solar storm so that we can actually, so there are different levels of forecasting because there are too many different interconnected things that actually um, boils down to this effect what we are observing on underneath the water. And so first of all, people try to understand sun, and they wanted to forecast what is going on the sun, let's say 24 hours ahead of time. And to be honest, it's significantly difficult. It's not like the reason is like we don't have enough data. Even with all these solar Parker Solar Probe and everything else, what we have last 50 years, the problem is the data gap. We don't have enough data to predict what type of sun we can think about tomorrow morning, what is going to happen in terms of magnetic and electrically. I'm not talking about the brightness of the sun. So so that is too small. But yes, scientists are still like trying to understand or forecast based on some sort of, there are physical model, there are numerical models, and also recent times, last 10 years or so, people started using neural nets to understand what type of sun they are going to see maybe 24 48 hours ahead of time. Regarding their forecastability, I would say some of them in the publication this do say significantly good, but the problem is with those scientific journals is like, I don't want to name anything, but what happens is like most of these papers, they can forecast the quiet sun very well. And what we are thinking about, these are one of a decade or maybe probably one of a 100 years event. And if you miss them, then you are going to cost millions or billions of dollars. So that is, we have still don't much idea whether we can confidently trace them, each individual of them every time, because eventually we don't have 100 years of uh, we do have more than 100 years of data, but what I'm talking about is like we don't have how much data cadence right now, let's say last 10 years or 20 years. With that data cadence, we don't have 100 years of data or maybe 200 years of data that might need it, or maybe more than that, I have no idea. On top of that, how much data you need to actually successfully predict each 100-year event or maybe 1,000-year event, which is like significantly higher. So that is one. And the second part, so that's the one part of the structure. And the second broader part of the whole forecast is like we need to understand how the solar wind or the sun, the things coming from the sun, is actually modifying the magnetosphere ionosphere system. Because in itself, if you think about it's a filter. These things are different filters, and we don't have a complete understanding of this filter response. So even if you completely understand the sun, let's say, which is again itself in itself is a very non-trivial problem, you need to understand what is going to happen with the magnetosphere ionosphere system so that you can actually predict those current systems, which is one of them is like the aurora. Response of this one of these current system is an visible aurora. So you need to understand that. So people are also trying to do a study on magnetosphere, ionosphere, their interactions with the solar wind, their interaction within itself, the feedback between them. And so with those things in hand, you can actually forecast again, like maybe going back 20, going ahead of 24 to 48 hours. You can forecast how much this current system is going to do. Let's say if a CME of 100 years worth of 100 year, one of 100 years event is coming tomorrow, how the magnetosphere is going to respond, or ionosphere is going to respond, or these current systems I just talked about, they're going to respond. So then again, we have limited by our understanding also data and numerical models. But yes, people are still doing significant job, and I would say like there are maybe before like 10, 20 years ago, and what we have right now is a significant advancement. Um, then finally, what I am doing right now is like if you completely know this ionospheric structures or current structures, whether you can understand how this induction is happening, because it's again it's a non-linear interaction. It's not only governed by the if you know the ionospheric current completely, you can completely forecast how much current is going on the induce how much current is going to induce on this long distance wire. You need to understand the earth structure, the frequency component, and everything else. So yes, there are different levels of prediction models are available, and they do a significant. I'll put it like they do a significantly good job going back compare it like 20 years ago, but it's still lacking, and we are not exactly sure we can completely forecast one of 100 or one of 1,000 year event that create a millions or billions of dollars of problems. So, for example, you might not need a significantly large event to create $1 billion or maybe a hundreds of $1 million impact. Back in 2022, I forgot February, there was a small geomagnetic storm. Again, people can you can Google it. It happened, and SpaceX lost almost 49 or 47 of their uh, satellites. They deorbited. And yeah, I don't want to go into the physics or something else what's going on, but the main concept is it's like even if you so the NOAA people actually predicted there is going to be a G1 storm going to happen in a couple of days. They predicted it, they successfully predicted it, but we didn't have enough understanding of this magnetosphere ionosphere system I was talking about, so that you can actually run a forecast model and you can actually say, oh yeah, there is a warning, you should not launch right now. They launched it, the SpaceX, on the 4th or 5th of February, something like that, and there was a storm. And due to this thermospheric effect, almost 49 or 47 of this satellite you got deorbited like within few minutes. They got LOS, loss of signal, and then after a while they find like they lost most of them. Yeah, and I think SpaceX actually uh, put a notice or like news like they lost almost $100 million or something.
Can you explain, because the part of the podcast is about the specific thing, which is, can you explain where the money is going for your project? What is it going on? Uh, is it travel,
Travel
salary,
and
these kinds of things?
salary, these kinds of things. It's so for this specific project, we got a funding card. First of all, we got a funding card, and that's a significant one. And then most of the fund is channeling to undergraduate student and for salaries. It's traveling, it's not much because we don't actually, what I am doing, it's mostly numerical modeling, understanding, and forecasting. It nothing to do with the like laying down an underground cable or maybe underwater cable or something like that. We already got some breakthrough to communicate with some of the submarine cable operator who can provide us the data with, so that we don't have to hassle about funding to raise money for that. And that would be a next step for us. So right now it's only like salary for undergraduate student and myself and some of the other collaborators in the project. Yeah.
Okay, and out of my own personal interest, I like to always end on this question, which is, how did you get started in science? What got you interested in, and how did that lead you on this path?
Like this specific study, or like
Oh, no, just science in general.
in science in general? Well, just questions, I guess. Nothing much. It's like a very general answer. I'm just curious. So one thing I can tell you from my own experience is like I work in electromagnetic field in the field of electromagnetism. Back in my undergraduate days, I really didn't like electromagnetism. So maybe that's the one trigger point. So I did my PhD and everything else. They have very specialized in space weather and these kind of things, but in fundamentally what I do is like a specialized version of electromagnetic field studies. So yeah, probably I struggle a lot in science and I have a question. So that's how I yeah got into this field of study.
All right.
Yeah.
Well, thank you very much for joining me. I really appreciated the chat. I thought it was great. So I'm very grateful for you for coming on.
Thank you for having me. Hope like your audience didn't have to Google all these word around in each like 10 seconds or so. Probably I tried to explain and try to keep it as simple as possible. Yeah, so that people can at least understand what is happening. Yeah.